So now's the second hard part of the lecture, and then after that it does get easier. So yeah, bear with me. So we're going to start talking about geochemical data, and most of this lecture is going to be about major and minor elements, but I'll talk a bit about what trace elements are as well, so we know how to divide these up. So as I kind of mentioned at the end of the last section, real rocks contain more than 3 end members. We can't just describe everything by some mix of diopside, forsterite, and anorthite, or forsterite, anorthite, and quartz. So these are great for explaining concepts, but when it gets down to the nitty-gritty of basalt crystallization, some of you will have seen in the thin sections in the last practical that we have some things like iron titanium oxides, the olivine, they're obviously not all pure forsterite. We have some iron, which also goes into pyroxene oxides. And then, of course, the plagioclase, we did look at a plagioclase binary, but when we look at this ternary diagram picture, we're just dealing with anorthite. So we're missing some of the complexity from real rocks here. So one thing we can use to help us understand differentiation a bit more broadly is geochemistry. And just to help us talk about things, we kind of divide the elements that you find in rocks into 3 main categories. These are major elements. These are usually more than 1 weight% in a rock. We have minor elements, which are between about 0.1 and 1 weight%. And then we have trace elements, which are less than 0.1 weight%. So the implication of this division is that major elements and sometimes minor elements are major components of minerals. So if we change the major element composition, we're usually going to change what's crystallizing. The trace elements are generally in too small quantities to actually make new minerals, so they kind of just sit in some of the existing minerals. And so the minerals are being controlled by the major elements, sometimes the minor elements, and the trace elements are just along for the ride. When we report major and minor element data, it's usually reported as weight% oxides. Actually, just 1 second. Okay, I did get that going. And so this is a big table, but I will talk you through it. Things that are a major element in one rock type might not necessarily be a major element in other rock types. So here I've given a few major and minor element analyses for some different rocks. So mantle peridotite, an ultramafic lava, a typical mid-ocean ridge basalt morb, an andesite, and rhyolite. So here we're getting generally more evolved from mantle down towards rhyolitic lavas. So you can see that silica is a major element in every single one. But something like titanium is actually a minor element in mantle peridotites or ultramafic lavas, but it's a major element in mid-ocean ridge basalt. Something like chromium is a minor element in mantle peridotites and ultramafic lavas, but it's a trace element in many basalts, and there's basically none of it in andesites or rhyolites. And I could go on, but yeah, so generally there's changes in composition between different rock types, and that also means that what is counted as a major element or a minor element or a trace element will change as well. So a couple of things to notice, aside from all these different elements that we use to describe the composition, you'll often see the sum, the total reported with it. And the reason we do this is usually these different elements are measured independently. And so it's just like a quick check. They should add up to 100%, right? There's 100% of stuff in a rock. So if we get totals that are much higher than 100% or much lower, that can sometimes be a cause of concern. Might mean that your data's crap. The other thing to notice is that iron has multiple valence states. So we have different oxidation states. So we can either have it as iron 2+ or iron 3+. Iron 2+ is usually reported as FeO. Iron 3+, Fe2O3, and this is because oxygen's 2-, so you need more oxygen to balance out the pluses in Fe3+. And sometimes these are reported separately, but that means you have to measure them separately. In a lot of more modern methods, they're just kind of lumped together, and that's because the methods we're using don't distinguish. So then either reported as FeO-T, so this is, we assume that all of the iron is in a 2+ state, and then we give the composition, or Fe2O3T, which is just saying total, so we assume it's all in a 3+ and give it like that. So you might see it reported in these different ways. Volatiles, so these are things like water and carbon dioxide, sometimes they're measured independently and they'll be reported, so you'll see H2O, CO2, maybe even sulfur. But sometimes they're reported as this loss on ignition, and literally what you do is you take powder of the rock and you heat it up in an oven, you weigh it before you heat it up and after, you find out how much mass has been lost, and that is about the amount of your volatile. So you'll see it reported as LOI, loss on ignition. And I think, yeah, this was in the...
LOI meaning loss of...
Loss on ignition.
On ignition.
Yeah. But you can just think of it as total volatiles. Yeah. Yeah, for historical reasons, these are all reported as weight % oxides. So usually what's happening is we're measuring, magnesium, and then we just assume that every magnesium has an oxygen attached, because we need to, the charges have to be balanced, otherwise, you'd get a shock from touching rocks, which we don't. All right. So the main point of that is that we can quantitatively, so with numbers, describe the composition of a rock using geochemical data, and we broadly divide the elements into major, minor, or trace elements based on the concentrations. We generally report major and minor elements as oxide percentages. Any questions from that? Okay. I wanted to talk a bit about the relationship between mineral compositions and major element data, just so you can kind of see where we're getting this from. So far, in this course at least, we've been talking about mineral formulas using these N members to try and describe different solid solutions that are possible. So, for example, in all the phase diagrams, I was talking about olivine as forsterite, Mg2SiO4, that's the magnesium N member of olivine, and we've also talked about, you can describe it as a forsterite content or an Mg number. So this is how much of it is forsterite, how much of it is phaolite. We also talked about plagioclase, and we gave this mineral formula, and we've talked a little bit about how you can describe feldspars as albites, anothites, orthoclase, so calcium, sodium, and potassium plagioclase. Yeah, and we've talked about pyroxene being in this quadrilateral, so all natural pyroxenes, or at least most of them, fit in this quadrilateral between enstatite, between something that has 50% wollastonite, so this is diopside, ferrocylite, this is the iron-rich orthoproxene, and this kind of clinoproxene is calcium and iron. So what we're talking about here is we're talking about proportions in terms of the number of ions of magnesium or iron or silicon or calcium or all these things. We're not talking about weight percentages. So we need to think a bit about how we convert between the two. So we'll start with probably the easiest case, although it looks a bit messy on the slide. And this is how you would calculate an olivine composition from Mg number. So what we're going to do is we're going to calculate a fertile mantle olivine. We said before that olivine in mantle peridotite is usually about Mg number 89. And we know that the olivine formula is Mg or Fe2 SiO4. So if we think about that, if the Mg number is 89, 89% of this MgFe bracket is magnesium, and the other 11% is iron. Because we've got two of them, we can write out the formula as Mg 1.78, beautiful, Fe 0.22, SiO4. And remember that the Mg number is 100 times the number of magnesium ions in moles divided by the number of magnesium ions plus the number of ions. So all we do for this is we break it down into these different components. We know how much of each one of these components we have, and then we just multiply them by the molecular mass of each of those components. So 1.78 MgO, and Mg has a mass of about 24, oxygen has a mass of about 16. So we just do 1.78 times the sum of these two. For iron, we do the same thing, but we only had 0.22 ions, and iron is a bit heavier, so iron's about 56. And then for silicon, it's a tiny bit different. We know that silicon's going to be 1 in olivine, right? Because it's the only thing that's sat in this site here. So we put a 1 there, and it's different because we have 2 oxygens for every silicon. So we have to make sure to multiply the mass of oxygen by 2. So when we calculate these, we're doing the mass of the overall component. So 1 silicon atom plus 2 oxygen atoms. This gives you the relative mass proportions. So we'll get some numbers that don't really mean much here. We have 71 in iron. We have, I think, yeah, these two are the wrong way around. MgO should be at the top. So we have 71 in, yeah, go ahead, Leonard.
So why 2 oxygen, why not 4 oxygen?
Because actually, the magnesium and the iron also need an oxygen. So if we wrote this out properly, it would actually be MgFeO times 2
Great.
SiO2. But usually in these mineral formulas, you just dump all the oxygens at the end to make them a bit less messy to write out. So yeah, sorry, this is the wrong way around. So MgO, we have 1.78. We've calculated this molar mass from this sum, and we just times these together. We get a relative mass, and as I said, this doesn't mean anything on its own. We do the same thing for FeO, and we do the same thing for SiO2, and then we basically just add up all these relative masses and divide each one of these by the sum of those relative masses, and that gives us our weight percent oxide. So a mantle olivine with Mg number 89 is about 49% MgO. It's about 11% iron, and it's about 41% silica. Okay? Everyone with me?
Yes, just to make sure, there's a misspelling in the, it says MgO. MgO is the top line, right?
Yeah. I'll change it on the version of the lectures that I'll
Okay.
repost them. Yeah. All right. Now we can do the opposite, and this is actually a lot more normal, right? It's when we measure an olivine composition, we don't usually have a machine that just spits out an Mg number. So usually we're going to get a composition in terms of weight percent oxides, and we want to convert that into a mineral composition to make it a bit easier to discuss and work with. So this example, this is a real olivine analysis that I did. So we have about 40% silicon, we have about 19% iron, and we have about 43 weight percent magnesium, and they're all oxides, right? There's also some minor trace elements that will come out in the analysis, and we're just going to ignore those because we don't care. So the question here is, could that have crystallized from a melt that was in equilibrium with mantle olivine? So to do that, we want to find the Mg number. This is the opposite way around, and because we don't care about the silicon when we're calculating Mg number, so we can just ignore it if we want to. But here we divide the weight percent by the molecular masses, so it's just the exact opposite procedure from before. So 38% magnesium, divide by a mass of magnesium oxide, that's about 40. 19% iron oxide, and we divide it by the molecular mass of iron oxide, which is 56 plus 16, it's about 72. Yeah.
Why is the magnesium 37 if that calculation is 43?
It's a very good point. I think I miswrote that, so I'll have to go change that as well.
Okay, just
Yeah,
making
yeah.
sure there's some.
Yeah, sorry, yeah, so this should read 43, yeah, absolutely.
Okay.
Yeah, and it's right in this table, so I don't know what's going on there. Yep. So, and then we stick it in this formula. So what this is doing is this is giving our relative molar mass. So we're getting rid of the weight percent here by dividing by this mass. And same with this one. And we can actually see that we get an Mg number of 0.8. So this is a more evolved olivine. The melt did not come straight from the mantle and then just crystallized olivine. Okay. So yeah, the way we do this, got our oxide percent, divide by the molar mass, that gives us our relative moles, and then we just stick these in. So 1.07 divided by 1.07 plus 0.26. And that gives us our mg number. Now I've gone a bit further here, and you can calculate the overall formula. And this is good. Silicon should be 1, and iron plus magnesium should be about 2, right? Because of our formula of olivine. Yes?
How does 0.8 tell you that it's not?
Oh, because we said the mantle olivine is about 89, right?
Oh, okay.
So going back to that olivine binary before, if it melted in the mantle, relatively shallow, popped straight up and crystallized olivine, it should also be about 0.89. Yeah. Okay. Now, it's more complicated for other minerals, but the idea is basically the same. So if we wanted to convert pyroxene analyses into this pyroxene quadrilateral, basically this is nice and simple. The only elements we care about are iron, magnesium, and calcium, because silicon's staying the same. All of these are, you know, Si2O6. This one's been simplified to SiO3, but it's the same. So we always have one silicon for every magnesium, iron, or calcium. So we can just ignore that when it comes to calculating the formula. So we have this big composition with all these different elements that are involved. We can check the totals. These are half-decent analyses. Yep.
Why has that one been simplified and the others haven't?
I think it might be to do with the structure of wollastonite, because wollastonite's not a pyroxene, right? So pyroxenes have those double chains. They have, yeah. So I think that's the reason why, but I'm not quite sure. Yeah. So yeah, all we do here is we take each one of these and we divide them by the molecular mass. So we're dividing MgO by about 24 plus 16. We're dividing FeO by about 56 plus 16, and I can't quite remember the mass of calcium, but it's something around 40, so we're dividing that by 40 plus 16. This gives us our kind of relative amounts of calcium, magnesium, and iron, and then to turn that into wollastonite, enstatite, or ferrocylite, these N members, we're just taking each one of these and dividing by the sum of all of them. So we do our CaO divided by CaO plus MgO plus FeO. Same on this other one. Now you can see here that if we plotted these up, we have one that's got about 37 wollastonite. So if we follow up our calcium mole percent, 37, something like this, it has about 52 enstatite and about 11 ferrocylite. So it's somewhere in here, it's an augite. So this is a fairly standard augite analysis. So it's got a fair bit of silica, it's got a fair bit of calcium, bit of MgO, and then a little bit of iron. The second one here gives us wollastonite only 4%, 84% enstatite, and 13% ferrocylite. So that's plotting right down here somewhere. So this is a magnesium-rich orthoperoxene. And again, this is fairly standard for orthoperoxene. Orthoperoxene has higher silica than clinoperoxene usually. It's got barely any calcium in it, very, very low compared to the clinoperoxene. We have more magnesium, we have more iron, okay? The last one we'll look at is feldspar, and this is exactly the same idea as with the pyroxenes. We can describe the feldspars by these potassium N member, sodium N member, calcium N member, and these are orthoclades for potassium, albites for sodium, anorthite for calcium. And so we only care about these ones, right? If we think about our feldspar analysis, we are basically swapping whether we have a calcium, a sodium, or a potassium. And the only difference is that with the calcium one, we have to swap a silicon for an aluminium. But if we assume that every calcium is going to have an aluminium, we don't need to worry about that when it comes to calculating the N members. So same thing again, except a little twist here is when we use the molecular masses for sodium and potassium, because it's Na2O, we actually divide it by 2. We want to have the mass per sodium. So for calcium, we just do the molecular mass, which is about 40 plus 16, so that's 56. For sodium, we do sodium divided by 2 plus, we do sodium plus oxygen divided by 2. So half Na2O is Na1, oxygen 0.5. I know that feels a bit funky, but if you remember just to calculate them for one of the kind of metal ion, then it gets a lot simpler. Because when we deal with stuff like aluminium or phosphorus, those are Al2O3 or P2O5. You just divide those by 2. So yeah, we're doing it per sodium ion, so sodium plus half an oxygen, and same with potassium, potassium plus half an oxygen. And again, we get our relative calcium, relative sodium, relative potassium. On their own, these don't mean much, but then we calculate calcium divided by the sum of all these three, that's our anorthite, sodium divided by the sum of all these three, that's our albite, and potassium divided by the sum of all these three, that's our orthoclase. So for these two different feldspar analyses, you can see the plagioclase is pretty high in silicon, but not quite as high as the potassium feldspar. We've got a whole crap load of aluminium, fair bit of calcium, fair bit of sodium, and very little potassium, right? So this is anorthite 58%, albite 41%, and very little orthoclase. So this is sitting somewhere in here. This would be, your labradorite, but again, don't worry too much about the name. It's a plagioclase. For the potassium feldspar, we get anorthite 11, albite 48, orthoclase 41. So we do have a little bit of calcium, but not a crazy amount, and it's sat somewhere in the middle of here. So it's kind of in the middle of the alkali feldspars, quite close to this boundary probably. The potassium feldspar, really high silicon and really high potassium. Okay. Yep, so aside from just using these mineral formulas, we can describe the mineral compositions in terms of major elements as weight percent oxides. To go from a mineral formula to a weight percent oxide, you need to multiply by the molecular masses of the different oxide components. Then you need to do some kind of normalization. And for going from the weight percent oxides to the mineral formulas, it's the opposite. You divide by the molecular masses. Yeah.
In the previous diagram,
yeah.
The miscibility gap, is that a composition that isn't possible?
Yeah, it's not possible. And the size of this gap changes with temperature. But basically, you will never have a feldspar that's 50% orthoclase and 50% anorthite. They don't sit together. Yeah. All right. So is everyone okay with those? Yeah.
The pyroxene diagram. You have two different numbers on each side of the triangle.
Oh yeah.
Because they just correlate, so 30% would always be 70%.
It's not that actually. It's basically the same lever rule thing we were talking about before, or plotting on a ternary diagram. So this one is the magnesium mole. So if I draw, because magnesium is at this corner, this is 100% magnesium. This is 90%. This is 80%. This is 70, right? So these are just to help you kind of draw it on and visualize. So when we get up to here, we've got 0%. And anything along this boundary has no magnesium in it, right? So our magnesium mole is going from 100 at this corner to 0 up here. Opposite for the calcium mole. And when we're anywhere along this boundary, we have no calcium. So here we've got 100%, here we've got 90%, here we've got 80%, here we've got 70. These are just to help plot or read off the data. Yeah. All right. Okay, geochemical variation diagrams. So you probably saw, like, when I plot it all up on a table like that, it's not immediately obvious what's going on. So what we usually do is we try and plot up our geochemical data, and usually we plot several different major or minor elements, or even sometimes trace elements, and we're plotting them against something called a differentiation index. So differentiation index is something that changes systematically as we differentiate our magmatic suite. Okay, it's usually magnesium, silicon, or you can use the overall like bulk rock or bulk composition Mg number. Magnesium oxide or this Mg number are generally better for mafic rocks, and silica is better for felsic rocks. I'll talk a bit about why in a sec. I've put up an example here of some really, really nicely well-behaved geochemical variation diagrams. So this is not usually the case. But what we can see here, if we plot aluminium against magnesium, we can see that as this suite of lavas crystallized or evolved, the aluminium and magnesium were varying in a systematic way, right? Here it's an incredibly straight line, and if we extrapolate that line out, it actually points to olivine. So what's happening here is this is what we call the olivine control line. Just olivine is crystallizing, and we're changing the composition of the lava away from olivine. Same goes in the titanium one, but by picking different elements to show, we can actually show different aspects of the lava crystallizing. So here I've plotted, this is FeOT. The reason it's 0.9 is that's to do with how oxidized the lava was. You know, I said some of it can be as Fe2+, some of it can be as Fe3+. And so this is just a crude correction, so we ignore the Fe3+. But basically, we look at that exact same line, and we can actually plot up the olivine compositions on this diagram, and we can see that this line points at an olivine with a magnesium number of about 0.90. So this is the average composition of olivine crystallizing, right? And it's here, this red line is kind of where we estimated the parental lava to be. So some of the samples have had olivine crystallized and removed, moves it away from the olivine. Some of them have actually gained olivine crystals. So they're slightly cumulate. It's a lava with, say, more phenocryst than it should have had originally. It's picked up some olivine from somewhere. If we look at a different element like chromium, we can see that chromium is actually dropping also as the MgO goes down. So as we're removing olivine, we're also removing chromium. If we plot the olivine compositions, there's not enough chromium to explain this trend. So we have another mineral phase, and that's chromite. You can't see it on this diagram because chromite's got like 50% chromium oxide, and it just wouldn't fit on the scale. Yeah?
I think I have a problem understanding how you can tell which way it's going.
Yeah, so that's why this differentiation index comes in handy, and I think this is the next... No, I'll talk about it now then, yeah. So the reason we use MgO in Mayfix is because usually the first phase to crystallize is olivine. So when we crystallize olivine and remove it, we go down MgO. So this differentiation index is basically like a proxy for down temperature for more evolved lavas. With silica, it's the opposite. The more evolved it gets, the more you get towards like andesite, rhyolite, that kind of thing, then the higher the silica is getting. So we use these indexes as kind of like a shorthand for like, are we going up or down temperature? So here, yeah, generally lower MgO, down temperature, more evolved, more crystallization. And again, you can see it in this one. It's the same as the phase diagrams when we talked about like if I pull something out of a melt, I push the melt composition away from it. So if I'm removing olivine, then the melt is going to go this direction, right? I'm taking olivine out of the melt, so the melt composition moves away from that olivine.
But you also said some olivine, there was
Yep.
some olivine being picked up.
Yeah, don't worry about this too much, but basically we tried to figure out what the parental melt was, and the parental melt had less MgO than some of the samples.
Okay.
So that would have excess olivine. Do you remember the pillow basalt sample that we looked at in the practical? It had like that weird rim of like olivine phenocryst. So that little area there, if you did a geochemical analysis, it would have more MgO than the rest of the rock. So it's picked up olivine. So yeah, we won't go too much into how you calculate these parental melts, but just be aware that melts can gain crystals or lose them. And in the extreme case where you gain a lot of crystals, you get accumulate. And in the extreme case where you drop all the crystals, you might get like a very glassy basalt with few phenocrysts. But most rocks are somewhere in between those. All right. So actually, here we go. Just like phase diagrams, when we crystallize a mineral, and these are just kind of general, this is from the textbook, two oxides, RO and MO, who cares what they are. When we crystallize this mineral, and remove it, we push the melt composition away from that mineral. So yeah, this is just showing multiple stages of removing this same crystallizing mineral, gradually move in that direction. if we have two minerals crystallizing together, then the melt will move away from what the average crystallizing composition is. And this is like a weighted average. So if you had like 93% plagioclase and 7% clinopyroxene, it's mainly moving away from the plagioclase, but also a little bit from the clinopyroxene. So you do some sort of weighted average based on what's in there, and that gives you your average crystallizing composition. The melt is going to move away from that composition. We can have more than two minerals crystallizing, so if we have three, then again it's the same, this kind of like weighted average crystallizing composition. So if we have olivine, clinopyroxene, and plagioclase crystallizing, then the bulk composition of the mineral assemblage can lie anywhere inside this triangle. So if it was 90% olivine and 5% of the other two, it's going to be somewhere down here. If it's 95% clinopyroxene, it's going to be somewhere up here. If it's like, 30, 30, 30, it's going to be right in the middle of the triangle. So, yeah. If we think about this trend, so the blue diamonds here are bulk rock compositions, it is actually possible to produce this trend from just a pure mixture of plagioclase and olivine, right? Because I can make a mixture which is maybe like 70% plagioclase and 30% olivine, and if I remove this, then I'll push the melt away from that.
If you remove what?
Something with 70% plagioclase and 30% olivine, right? It's that same thing that I was doing before. I point away from the mixture, which is where my thumb is there, and I'm going to move that way. But I can also do it with this overall, three mineral mixture. Either one works. What I can't do, I cannot produce this trend with mixtures of just plagioclase and clinopyroxene, right? Because no matter how I organize this, I can't get it to point on the same angle as the line, right? I can't. So we need to have, so from this kind of diagram, we can see that we either have plagioclase and olivine, or we have a mixture of all three. So this is where petrography would be needed. Yes?
So what would the trend line look if it was just plagioclase and clinopyroxene?
It could be pretty close, right? It could be like that. If I had 100% clinopyroxene and no plagioclase, that almost fits. Or it could be anything away from that. So, if I was 50% plagioclase, 50% clinopyroxene, and I started here, I'd actually be moving this way. So we're always pushing away from whatever's crystallizing. Okay, yeah, so I probably should have put this a bit earlier. So why do we plot against magnesium, silicon, and Mg number? When we're crystallizing ultramafic or mafic magmas, a lot of olivine, a lot of pyroxene, both of those drop the MgO. And if we look at it really kind of crudely, as we go from a mantle peridotite to an ultramafic lava to a basalt, a morgue here, then the MgO here drops a lot, right? This is a huge difference. Whereas the silica's basically not changed. So silica's pretty useless for mafic magmas. But once we get down anything past a basalt, if we have an andesite, a dacite, or a rhyolite, we just don't have that much MgO left. It's all been removed in olivine, pyroxenes, it's gone. So across this kind of change in composition, the MgO is barely changing. But the silica is going from about, high 40s, 50%, all the way up to 70%. So silica is much more useful for felsic magmas. Yep. So if we're using MgO or Mg number, they decrease with increasing differentiation. If we're using silica, it increases with increasing differentiation. And I've put these kind of like rough guidelines for mafic magmas, and I think these are just, rather than, I'm not necessarily expecting to remember every mineral formula, but you kind of need to have an idea of how different minerals are going to affect melt compositions when they crystallize. So just some really, really rough guidelines here, but if you remove minerals which have high concentrations of certain elements, then those elements are going to fall in concentration in the magma as it evolves, as it continues to differentiate. So if we're removing plagioclase has really high aluminium, aluminium's going to fall. If we're removing clinopyroxene has really high calcium, then calcium's going to fall. And if we remove olivine, which has high MgO, then the MgO is going to fall. And this is also a nice little petrography reminder, because some of you are addicted to cross-polar light, so you can tell an olivine without actually putting the polarizer in, because it's got those curving cracks, high relief. Here's an augite. This is a clinoproxene with a twin, and then in your feldspars you've got that characteristic lamellar twinning. The other thing, there are also some trace elements that fall when these things crystallize that can also be quite useful for identifying what's going on. We'll cover these in a later lecture, but olivine takes up a lot of nickel. Plagioclase takes up a lot of strontium and europium, but more on that later. During mafic magma crystallization, a lot of other elements are incompatible. So these are not being incorporated into the crystallizing minerals, so they tend to go up with differentiation. So for example, titanium, potassium, or phosphorus, these are all kind of incompatible at first. Titanium starts to go down once we crystallize iron titanium oxides. So some of you would have seen those in the basalts in the practical. So these are kind of like these usually fairly big, opaque grains, a bit weird shapes. Potassium keeps going up until you crystallize something like potassium feldspar, which we can recognize from this cross-hatch twinning here, or biotite in some magmas. And phosphorus keeps going up until something like apatite crystallizes. So apatite is a calcium phosphate mineral. Yeah, sodium is a bit of a weird one because it is incompatible early, even though we're crystallizing plagioclase. And the reason is that the plagioclase that we're crystallizing from mafic magmas is more like anorthite, doesn't have a lot of sodium in it. So even though we're removing a bit of sodium, we're removing more of everything else. So we actually end up concentrating sodium in the melt that's left over. All right. So these diagrams allow us to show us a lot of data very quickly, usually plotting different elements or oxides against a differentiation index that tells us which direction the magma crystallization, evolution, cooling is going. And the magma composition is always going to move away from whatever is crystallizing, whether that's a single mineral or some combination of minerals. All right, does anyone have any questions on that bit? Okay, good. Seems like geochemistry is easier than phase diagrams, so that's good. All right, I just have an example here of how we can use this, and I tried to look at more because it's what we were talking about last week, and I thought it'd be familiar for all of you, but it's actually quite difficult to do, so we'll try and work through it. But this is mid-ocean ridge basalt from the East Pacific Rise. This is a fairly classic, fast-spreading ocean ridge. We get lots of basalt that kind of looks very similar. So this is just an example from a paper where they plotted geochemical data from every morb that they could find in a database from the East Pacific Rise, and they tried to compare this to geochemical models. And we're not going to use geochemical models, but this actually kind of helps get your eye in and see what's going on with the crystallization. So there's three main stages of crystallization in these. The first one, although we don't really see it in this data, there's a period where we're just crystallizing olivine. So this is above, say, 9%, 9-weight percent MgO. So in the titanium diagram and the sodium, actually in every diagram, all of these other elements are just going up because we're removing olivine. Olivine doesn't contain any titanium, it doesn't contain any aluminium, doesn't really contain any calcium, and doesn't contain sodium. So when we remove that from the melt, we're concentrating everything that's left in the melt. So we move away from an olivine composition, which maybe has 50% MgO, it's way off these diagrams, and we push them out in this direction. The next thing to crystallize is plagioclase, and we can see that because the aluminium starts to drop, okay? And the MgO is still dropping, so plagioclase doesn't have any magnesium in it, so we must still be crystallizing olivine. So we're crystallizing olivine and plagioclase. This moves us down in aluminium. It kind of flattens out the curve a bit in calcium, and in titanium and sodium, nothing really happens. It sort of steepens them a bit because we are removing plagioclase, which has less sodium than the melt, and it's got no titanium in it. So we've got some combination between olivine and plagioclase, and it's pushing these other elements up in the melt, but we're now dropping aluminium. The final stage, which we actually can't tell what's going on from this diagram, but we'll try and figure out in a sec, is we're decreasing magnesium, we're still decreasing aluminium, but there's a kink. And at the same concentration, which is just slightly below 9% MgO, we start dropping calcium quite rapidly. So we know that clinopyroxene must have started to crystallize because we're dropping the calcium. We know that aluminium is still crystallizing because we know that plagioclase is still crystallizing because we're still dropping the aluminium. The question is, because clinopyroxene also has a fair bit of MgO, are we also crystallizing olivine, or is this just plagioclase and CPX? Yeah, so as I mentioned, both titanium and sodium just keep going up. The plagioclase isn't sodic enough, doesn't have enough sodium. The titanium doesn't have anything taking it out of the melt. So we can use the lever rule in geochemical plots just like we were in the phase diagrams. So on those 3 stages of crystallization, the first one was olivine. We don't really see it in this data much, so we don't worry about it. And the second one is olivine and plagioclase. Now, if we want to see how much of each is crystallizing, then we can plot up the compositions. So this is actually an average olivine from mid-ocean ridges. This is an average plagioclase from mid-ocean ridges. And we can compare this East Pacific Rise basalt data to these. So I've just zoomed in a bit because the olivine is way off and it's not very useful. Now, it's a little bit messy, but would you agree with me that this is kind of the trend that we're seeing when the aluminium starts dropping? More or less, yeah. So what we do is we know that second stage was olivine and plagioclase, so we project it backwards until we hit this line between olivine and plagioclase. And I helpfully marked it with tick marks every 10%, but this is basically the lever rule. So 10%, 20%, 30%, we're closer to plagioclase. So we've got 70% plagioclase and 30% olivine crystallizing. Okay, so that was our second stage. Now in the third stage, we had calcium dropping as well, so we know that clinopyroxene started crystallizing, but we weren't sure if there was olivine. I feel like what I've put on this diagram gives it away a bit, but this is kind of the trend I see in the second bit. It's fine if you don't agree with it, we're just doing rough ballpark. So after the calcium starts dropping, which was somewhere below 9%, it sort of flattens out in aluminium. Now if we project that back, it's possible, using the lever rule again, we're closer to clinopyroxene than plagioclase, and 10%, 20%, 30%, 40%. So we got 40% plagioclase and 60% clinopyroxene. But our bulk crystallizing assemblage could also have olivine in it. And from this diagram on its own, this is an example, right? We could have a little bit of olivine, some plagioclase, some clinopyroxene, lies in the triangle between those minerals. But we could also have, anything back here. So we actually need to go look at another element and do the same plot, and this will help tell us the answer. So calcium behaves differently to aluminium because it's high in plagioclase and clinopyroxene, whereas aluminium is only high in plagioclase. So again, looking at the zoomed out view, we have calcium against magnesium, we have our plagioclase composition, clinopyroxene, and olivine. And if we had mixtures of plagioclase and clinopyroxene, they'd lie on this line. If we had mixtures of plagioclase and olivine, they'd lie on this line. If we had mixtures of all three, they could be anywhere in a triangle between these. I'll just zoom in again. If we back project along this line, this is our second stage of crystallization. We've got olivine plus plagioclase, and then the calcium starts to drop somewhere along this line. If we project that back, we get 20% plagioclase and 80% clinopyroxene. That's different to what we were getting from the aluminium, right? So it doesn't fit because these are the same rocks. We can't simultaneously have 80% clinopyroxene and 60%. So it's inconsistent. So we can tell that we need something else. But actually, if we back project along this trend, we hit that same point with 7% olivine, 43% plagioclase, and 50% CPX. So that's kind of our answer, is we do need olivine crystallizing at this point. Yes?
how did you know to stop it somewhere in the middle there?
Yeah, I'll get onto that because I cheated a bit. But yeah, the point is that if we compare these different diagrams using different elements and we pick the elements that are sensitive to different minerals crystallizing, then we can get it so there's only like one solution, right? There's only one set of elements. It's like in that very first one that I showed you, we could explain everything with just olivine, except when we plot it against chromium, and then it had too much, the trend had too much chromium for just olivine. So we needed olivine plus chromite. This is the same. If we plot against aluminium, we can make it work with 40% plagioclase, 60% CPX. But when we plot against calcium, that doesn't work. So it's inconsistent. We need another phase. That's olivine. And yeah, that's where I got it from. This is back to the phase diagrams, this is the eutectic point of a basalt, is about 7% forsterite, olivine, 43% anorthite, and 50% diopside. So hopefully this shows the link between the two. Yeah, so we can do it, if we only look at one element, we can do it with just CPX and plagioclase, but when we start putting these different elements together, we can really narrow things down. Okay, oh yeah, last point. Why are geochemical data messy? I mean, so this is a big cloud, right? This is kind of a shit show. We're not getting these nice straight lines like in that first diagram that I showed you. And the reason is, we've been treating all this MORB data as if this is just like, you know, one batch of melt that just goes and crystallizes, and we're just removing crystals. That's when I do all these back projected lines, we're just removing crystals and nothing else. But in practice, real lavas have phenocrysts, so sometimes we've removed crystals, sometimes we've added some back in. We could have crystallized some, removed it, and then added in crystals with a different composition. It was a whole mess. So the example here is a pickrite. This is probably some sort of basaltic composition glass, but it's absolutely chock full of olivine, and it's unlikely that that is like a primary, you know, mantle melt composition. This is a basalt that got extra olivine. We also have these other problems like magma mixing, assimilation, alteration that can cause a lot of scatter. And in the MORB plots that I showed you, that was from like, you know, several thousand kilometers of each Pacific rise. So who's to say that all the melts coming in were this exact same composition? So often when you look at these, this geochemical data, it doesn't fit really nice like trends and stuff. So you have to have a bit of like you have to combine the geochemistry with the petrography, and you need to be careful about how you read it. All right. So yes, we can use different elements and compare the geochemical diagrams for all these to kind of like make a unique solution to what's crystallizing and how a magma suite is evolving. We can also use the lever rule, same as for phase diagrams, and it's really important to remember that the bulk rock compositions we see are not just one-to-one, they're not just melts, right? Does anyone have any questions on that? All right, we'll take a break there then. That's the lecture summary there, if you want to make notes. Another 5 minutes. I think the last lecture is quite short, so yeah.